Today we have the privilege of speaking with an engineer whose vision quite literally reaches new heights. Sebastien Besse is the mind behind one of the most audacious engineering concepts of our time, a 3,000-meter vertical tower. A bold idea that challenges not only our technical capabilities, but also our imagination as engineers. His article, published in the April 2025 issue of NAFEMS Benchmark magazine, titled Think Big, captured global attention for its fearless exploration of what might seem impossible. As a FEA engineer, we often operate at the intersection of precision and realism. But there comes a time when engineering is not just about solving current problems, it's about pushing boundaries, questioning assumptions, and mapping out a future that has never been built before. In this interview, we'll explore the genesis of Sebastien Tower project, the mechanical and computational challenges behind designing something of this extraordinary scale, and what it truly means to think big in today's engineering world. Whether you are a seasoned analyst or just beginning your journey in finite element analysis, Sebastian's story is a powerful reminder. The future belongs to those who dare to imagine it and model it. Thank you very much for joining this session of FEA Journey. First of all, thank you very much, Sebastien, for accepting the invitation to join this episode of FEA Journeys. As mentioned in the introduction, I'd like to dive with you into the origins of your ambitious 3,000-meter tower project and explore with you the mechanical and computational challenges involved in designing a structure of such extraordinary scale. So before we jump into the introduction, Sebastien, please, can you introduce quickly the 3,000-meter project to the audience?
Hi, everybody. Hi, Dominique. Thank you very much for the invitation to discuss here with you. Well, first of all, I have a lot of respect for the work you provide for the FEA community, in particular on LinkedIn.
Thank you.
I didn't have the chance in my career to work as a structural engineer for aircraft, but I've been always impressed about these jobs and the high level of safety required. Actually, about the 3,000-meter project, it's an idea I had almost more than one year ago now. And it was at a period of my life where we had a kind of familial crisis, and one morning I woke up and I had this vision of a tower in my head, and I was pretty convinced it was possible to achieve pretty high tall structures like that. And so I started to draw and sketch on papers and think about it. I first thought about 2,000-meter towers, and then I realized that it would be quickly some teams would find a way to do more than 2,000 meters. So maybe 3,000 meters would be great. And I started to do some calculation about it, and I convinced myself that it could be possible.
Okay.
So that was the starting point.
Okay, and 3,000 is a nice number for a tower. Okay, thank you, Sebastien, for that. So before diving into the mechanics and modeling, let's begin by understanding the vision. You see what I mean? Every great engineering endeavors begins with a bold idea, often sparked by curiosity, necessity, or inspiration. So to start the conversation, I propose we uncover the roots of your concept. So visionaries often draw from the past to shape the future. My question is, was your imagination steered by iconic structures like the Eiffel Tower? And how did that legacy evolve into the futuristic concept you're now proposing?
Well, to reply to your question, first, I have to say that I have a lot of respect for the legacy of Gustave Eiffel. Actually, the drawings of the Eiffel Tower are available online for free at the French National Library.
Oh, okay, I didn't know that.
And when I was younger, I've been maybe 3 to 4 times in Paris to visit the Eiffel Tower at the top floor at 300 meters. And
Yeah,
the view is incredible there, right? From
sure.
the ground looking to the top, it's unbelievable. And one of the questions I had was about the curvature of the steel columns, right? It's not straight, it's bended a bit,
Absolutely.
right?
Absolutely.
It's not straight beams. So why? And according to the drawings, it's curved. Plus, when you think about it, when they build step by step, I was thinking the dead load while building is increasing a bit the curvature, right? So you build, then it's falling a bit because there is the weight, dead load, right? And
Correct.
I think this curvature is necessary to limit the buckling on columns. It's kind of auto-stable, right? It means the vertical buckling can happen towards the vertical center line. It acts like an elbow in piping. It adds flexibility with thermal expansion, and this allows displacement, help to stabilize the structure. It's not the case for vertical building. On a 3,000 meter tower, it's very important that the base is larger than the top to reduce the bending stress due to lateral wind at the interface between the base plate and the concrete foundations, like for the Eiffel Tower, right? Or if you decide to do a vertical tower, then you need to have very resistant columns at the base, and then you can decrease the strength with the altitude, right?
Yeah. Because you don't take advantage of this shape, this curved shape. Okay, I see. Yeah, that's a very, very interesting. So yeah, so basically the Eiffel Tower, which is a very old concept, has been designed with the right thinking at the beginning. So it's like using what is working, even for a new project. Yeah, that's very smart.
And to add to what you say, it's very incredible that when you think about it, they did build the Eiffel Tower without electricity or AutoCAD or finite
You're
element
right.
modeling. They had
You're
really
right.
a knowledge from their hand, right?
Absolutely. Absolutely.
That's
Yeah. It's amazing to think about that. And it's still here. It's still a nice tower. As you said, we can visit it, we can go into the tower. So yeah, it's a great demonstration of the knowledge at this time. Yeah, you're completely right. So now let's move from vision to execution. The scale of your tower presents an amazing set of engineering challenges. So I would like we delve together into the mechanics, materials, modeling strategies, and the practical constraints that define your project. Not just as an idea, but as an engineering endeavor. Okay, so first, from a mechanical and structural standpoint, what are the most critical challenges in designing a 3,000-meter tall structure?
I think there are maybe 4 points that can be discussed.
Okay.
First of all, it's about the wind, right? It's probably the most difficult point because on such a high structure, you want to have really a high global area moment of inertia to get very low wind displacement at the top. For instance, on Eiffel Tower at the top at 300 meters, you have maybe 55 millimeters of lateral displacement when there is wind. And this can increase a bit if there is a storm, but this is, well, you can feel it a bit, but you're not throwing up, right? You can work. You can work there. You feel okay. People working in the Eiffel Tower at 300 meters, they can get a burger or whatever. It's okay. So this is important for for service, right? Second point is the buckling in terms of structure due to the dead load. So in particular on the first columns, close to the ground, there is such a huge weight that is accumulating from 0 to 3,000 meters. So how do you manage the risk for buckling? So that was one of the point I was working on, is that let's focus on the first 40 meters and see if we can design a system of columns that can handle 3,000 tons per columns at the top. So, and you had 4 systems of columns, so the 4 systems were able to handle 12,000 tons of pure axial vertical loads, compression.
Okay.
And so I think that's an important point, right? And how you transmit these pressures on the ground, on the concrete.
Yeah.
Also,
using a smart load path to the bottom of the tower.
Yeah. So you don't want to transmit to reduce the torque to the concrete using appropriate 3D design.
Okay.
Follow the rotation and this kind of stuff. Another point is this kind of structure, of course, has to comply with the law. And you know that the law and the regulations can impose many small details for papers and and lawyers, but for structural engineers, it can have consequences like you need to think about the walkways, the elevators, the numbers, the access, safety, if there is a fire, blah, blah, blah. And this has a lot of, you're adding weight, but you have to control the weight, because if you put too much weight, the column at the base just go nuts.
Yeah, here you are talking about additional weight you don't necessarily need for the structural integrity, right? Yeah, okay.
So you want to have sufficient margins, that's how we say, margins, so you can add some loads, because you never know at the beginning of the project if something like that has to be built. You want to have a safety values that you know, well, if we build this at this elevation, it's okay. But if you go up, stop. Another point is also the timeline, how you can build such a tower, in particular in terms of tower cranes and lifting, temporary scaffolds. How you integrate this into the design itself, how you bolt it, how you add it, remove it, the dynamics, right? The timeline. It's probably
it's a huge challenge. Oh my god. Yeah, I didn't think about that, but yeah, now as you mention it, I think it's a big challenge. Yeah, thank you. Very, very interesting. Thank you for sharing that, Sebastien. You mentioned in your article in Benchmark, the last edition of Benchmark, that a full 3D modeling is still out of reach for this project. Okay, so how did you break down the problem, and what tools or methods did you use to navigate those computational limits?
Well, not being able to create a full 3D model is frustrating, right? But as I've said, for Eiffel Tower, they use the pen and paper to do the drawings. Without electricity or the finite element method. And to do a good 3D modeling of the 3,000-meter tower, I think it has to be done in 75 models. Like you cut it and you split it in 75 models. Each one is 40 meters, 8 height, and from the bottom to the top, because it will be built from the ground to the top, right? And once the first 40 meters are built from 0 degree to 360 degrees. You continue from 40 to 80 meters and so on. But due to the weight of what you're building and the angle of the columns, it's not vertical, right? It's like that. So there is a deflection, right? It's due to gravity. So what you draw is not what you're going to, if you build the second level and you come and you try to bolt, it's not in front. I can't put the bolts here. It's not fitting. It's not
you mean it's not aligned?
So you need to once you build the first level, you have to a team has to come on site and to get the measurements and record the dimensions as built. And then you adapt the 3D model from 40 meters to 80 meters, and then you repeat this 75 times until 3,000 meters. I think having a full 3D model is not an absolute need. Sure, it would be cool, right? But cool. The most critical point is how do you double check the number of bolts, the size of the weld, the dimensions of the beams, if everybody knows the tension, shear, torques. So yes, also of course you need a at least in France, I don't know in Canada, but if you want to build something, it has to be approved by authorities, right? Regulations.
Sure.
So for that, you need a drawing and a calculation note. The calculation note has to prove that's what, and you need to have consistency between the two documents, right?
Yeah.
So of course, you need a calculation note, and then doing a multi-scale modeling is one approach among others to create a calculation note for such a tower. And if the design is good, the more you create models, the more you confirm the mechanical strength is okay. And yes, the thinking of the methodology upfront is critical.
Yeah, completely. Yeah, very interesting. So the idea is to do some modeling in order to achieve the simulation challenges. And geometry plays a critical role in performance. So how do the tower's geometry, especially the tower's cylindrical shape and the lattice-like framework, contribute to the wind resistance and the global stability of the tower?
That's a very good question. Actually, the lay structure is essential to reduce wind loads on the structure.
Right.
For instance, the Eiffel Tower is a lay structure, and it's still standing after 138 years. So it's possible, of course, it's possible to consider the worst case scenario where there is a huge volume of air blowing on the 3,000 meters from the ground to the top with a constant peak dynamic pressure.
Okay.
And in that case, I found that it could add 50% of local pressure at the top of the column at 40 meters. So it's bending, right? So it's bending. On one side, it's adding pressure, and the other side is reducing pressure. So of course, you want to know where you increase the pressure because you are more risk of buckling at that point. Even if this load case has been described as not realistic by a specialist of weather forecast, I think this load case should remain active for the design in terms of safety. About the cylindrical symmetry, it's coming from trees, as you know. The area moment of inertia is independent of the direction of the wind, right? But of course, a cylindrical symmetry is not mandatory, but it's a well-known geometry. And
as you said, nature is using this geometry, so probably it's a good geometry. Mimic the nature is always a great idea.
When you think about it, it's like it's the different forces from wind in different torsional movements and bending, and it's still. Well, sometimes it breaks, right? But it's pretty good.
You're talking about the wind, the speed, the wind acting on the tower. Is there any kind of regulation about the type of wind you have to consider on the tower? Is it really regulated, or how does it work?
Well, here in France, we use the Euro codes with a national annex that gives a logarithmic profile of speed from 0 to 200 meters of height. So, for instance, you cannot calculate the Eiffel Tower with the Euro code, right? It's not, you have the dynamic pressure profile available. But they did use Gustave Eiffel and his team did use some data, some hypothesis about it. Like I think it was something like 200 or 300 decanewton per square meter dynamic pressure, lateral pressure, which is a lot. It's
a lot of pressure.
It's pretty safe. When you look at the drawings of Eiffel Tower, you're like, well, wow. If I have to propose that to my chief of project or my client today, he's going to think that he doesn't have the money for that. He wants to optimize the dimensions of the steel, right? Excellent.
Thank you for that. So a project of this scale doesn't just test the current simulation tools. It highlights where they fall short and where innovation is needed. So now I would like to have a reflection about how digital simulation must evolve to support the engineering challenges of the future. So in that ways that advances, whether in algorithms, solvers, or modeling strategies, do you see as necessary for FEA to truly under structures on this scale?
This is a good question. I don't know. Sometimes for very specific projects like nuclear, for instance,
Yeah.
some toolbox or plugin are developed from a given software to facilitate the project. We could imagine a plugin with robust structural analysis SDK from Autodesk or
Okay.
ANSYS distributed by ForCAD could be helpful. Same for SolidWorks. A plugin could, for instance, check the match if you do 75 models, different height. You want to match the XYZ, every model of 40 meters for the connecting nodes, right? You want to be sure that you are the same. You have different files on a computer. You want to be sure you're matching, right, as the interfaces.
Correct.
So you could have a plugin for doing that, for instance.
Okay.
And be able
So,
to export the different pressures at these nodes and torsion, bending.
In order to load each sub-model with the effect of the upper or lower portion. It is
Be
what you
sure
mean,
to be in
correct?
the same XYZ directions without changing the direction and doing mistakes, numerical mistakes, which are very basics.
Yeah, absolutely. So if you had access to unlimited computational power, what would you do differently in your modeling approach?
Well, I guess I would build a detailed full 3D model based on 1D beam elements.
Okay.
Yeah, it would be easier to capture the resistance to wind actually.
Okay.
But not having access to such unlimited computational power might be safer with the use of more conservative beam dimensions. So, good question. But when you review the dimensions of beams used in Eiffel Tower, as I was saying, on a walkway, for instance, it's pretty safe. It's pretty safe again. It's,
Okay.
it's not the place to really optimize the weights that much, right? You really want to be very stiff and just put the steel you need, but not more, not less, right?
Just put the material where you need it. So
But that's all. That's all the difficulty I find in the industry and engineering, right? How you distribute some materials in space, right? How do you decide to put the geometry here like this, here cross, here T, here beam, or not?
But now we are lucky because we have access to some optimizations algorithm, some optimization software, which help us making that kind of decision. You see what I mean? I don't know if you had the chance to use such a tool for this project. Those optimization.
Not. Well, it depends the way what you think about optimization, but like if you take a big piece of raw material and you use some part of it, like
based on some constraints in terms of weight, deflection,
this
and
kind of
stuff like that.
algorithms I didn't. I know it exists in particular in aeronautics, right, or spatial, but no.
You didn't try that yet.
It's a good. Could be a great idea, in particular in spots where you want to reduce the loads, like in floors. We have to use multiple beams so people can walk on it. You might also here reduce concentrated loads.
The advantage I see with this kind of solution, optimization solution, numerical optimization, it is the fact that the algorithms help you to put the material where you need it based on on the constraint, So you're not going to put extra material where you don't need into the structure. So it is the beauty of this kind of application of solution, I should say.
Yeah.
So what message do you have for FE engineers who feel constrained by today's software or computational limitations? Because we face all the FE engineers face those limitations, you know. So, what message do you want to share with us about
Well,
that?
yeah, it's complex. It's difficult. It's a real pain. I know sometimes.
Yeah.
I work most of the time in the industry, including piping and pressure vessels,
Mm-hmm.
with a constant culture about risk. Uh,
Okay.
sorry. The best risk, yeah, the better risk is the one you don't take, right? Um, it, it's difficult to consider. Well, I've reached a good level now. I'm an expert because we
Mm.
constantly improve ourselves.
Absolutely.
If you practice a lot, you should get an excellent level, as long as your results are approved by your clients or peers,
Mm. Mm.
as long as they operate in good faith too, right? Because
Correct.
I can say, well, no, that's not a good job, and it may be a good job. Well, you know. And in my career, I've got an engineer diplomas and a PhD, and then I started as a mechanical engineer in design office in France. I've been
Okay.
learning a lot, in particular, talking with drawers first, and also with calculation engineers.
Mm-hmm.
It was important to me to understand not only technical things, but also how the market works, including sales and insurance. Um, Smart people have a lot of problems that stupid people don't. You know what I mean?
Well said.
When you're smart, sometimes you can have some anxiety. It's difficult to plan what you're doing because
Mm.
coming step is not that clear, but it's coming and you're safe. It's fine, but you know we have some problems, smart people, and they can feel more and have to manage many complex emotions too, right?
Yeah.
And I think being strategic is very important to success. I think a good balance between analytical calculations and FEA is a good path.
Mm.
Sometimes project sounds like, well, you have 4 days to make the equivalent of a PhD program.
Mm-hmm.
So ha ha ha, it's really hard. You have few time. It's so definitely the way you connect the dots is a critical path.
Yeah.
In FEA, you constantly improve your skills and methods, and little by little, at some point, you reach a critical point. You connect the dots, and you get to the new level, right? For instance, the first 5 years of my career, I've mostly worked with software using 1D beams elements and
Mm-hmm.
analytical calculations. And it's later that I started to use shell elements and combine them.
Okay.
Um, I don't like to say that, but sometimes the ones that succeed is also the ones who doesn't give up, right? Um,
Correct.
but I find there is also a financial component in all of this, and sometimes engineering companies have few money and for softwares and courses
Yeah.
to start with,
Yeah.
and convince your boss to invest might be your first project, right?
Yeah. Yeah. I see what you mean.
Um,
Yeah. 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 So yeah, very interesting. Thank you for that, Sebastien. You know, engineering has always been a blend of technical rigor and visionary thinking. But the courage to think big isn't always easy to maintain in a world focused on incremental progress. You see what I mean? So now I would like to explore with you the mindset, okay, behind pushing boundaries and inspiring the next generation of bold thinkers. Many engineers, we know that, focus on incremental improvements. So, what advice do you have for those who want to make bold leaps instead?
Well, I find it difficult to improve all on your own.
Mm,
Myself, I even often copied what I've seen and what I've heard. And when a human talks to another human, that's for
mhm.
me the best way to learn something.
Yeah,
So I did accumulate many opinions about a topic, and then time after time, then I can make myself a clear idea about it. It can take years, but I work like
mm,
that. But
mm.
once I'm sure about it, it's solid. Like, and there is this sentence that's always coming in my head when I'm calculating for our clients is that anything that is not stable ends up falling down.
Oh, yeah.
That's hard.
Yeah, yeah.
I think a good way to find shortcuts in your self-development is to try to get experimental data from your clients. I mean
Yeah,
feedbacks from
yeah.
what you've been designing
Mm,
to know how my calculation was accurate or not. Is
mm,
is that really stiff or in real life or not? Did it crack?
mhm.
If yes, how many years after?
Yeah.
Also because the calculation engineer might feel some pressure to optimize the thickness of the components to
Mm,
reduce the cost,
mhm,
but also increasing the it's also increase the displacement and then risk. So there is a
mm.
balance between optimizing and reducing risk, right? It's not.
Yeah, yeah, absolutely. Yeah, yeah. You're talking about bridging the design and simulation with the reality, which is not that easy.
Mhm. Yeah, and I think trying to see projects from A to Z. Like I love when my clients send me pictures. Okay, that was built. Here is a picture. Here's a pressure vessel. Here's the piping.
Hmm. Hmm.
That feels great. Right? I had a dad that was building houses, and
Hmm.
so I liked helping him with the rocks and So I like it to see when it's done, right? Not only just having files on my computer is not satisfying.
Yeah, yeah, yeah. I see what you mean. Yeah, yeah.
And also I would add that I to work on your spirit, feeling your intuitions, and take measure risk is also, I think, a good answer to your question.
Yeah, yeah, yeah. Thank you. Very, very good thought. I love it. So, what has this project taught you about the power of vision and perseverance in engineering? To conclude with this section of the interview.
Well, it's difficult to explain how at some point you can feel convinced that one design can work.
Mm,
You're working every day, you're calculating still, and
mm,
somebody like, well, if this can do that and this can do that, well, this design that I imagine now could work. Like you can
mm.
feel it, right? You're pretty sure. You run the calculation, and yeah, that's it. So I would say the path on projects is pretty nonlinear actually. Sometimes it's when nothing go right, turn left. But sometimes it only depends on your capacity to get the problem solved. So I don't know. I think
Sure.
curiosity is one dot to connect, I think.
Mm.
Now I'm 41, and sometimes I watch 3D and 6 models on YouTube, and I'm like, wow, how did they do that, right? That's so cool.
Yeah.
um, and also, I would add that there are so many softwares now on the market. It's so easy to lose your courage. There are so many things to learn, so little time.
Yeah, 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 right. That's true.
So,
Yeah, thank you for that. So, as we near the end of our conversation, the first part of our conversation, let's pause to reflect. So, engineering is not only about solving today's problem, it's also about shaping tomorrow's legacy. So, if this 3,000-meter tower were to be built one day, what legacy would you hope, sorry, it leaves behind for engineering, for society, and for the future dreamers?
well, I think building tall structures is done since a long time by humans, right?
Yeah, but not that tall.
I'm not the first one. I'm not the last one. And
Yeah, you're right.
yeah, people will continue to build higher and higher structures.
Correct.
I think it creates tourism, including the creation of jobs for the country where it's built.
Yeah,
Like, for instance, in Paris, Eiffel Tower is creating a lot of people coming.
sure, sure.
And but I would like to remain humble and acknowledge that this question is beyond me, Dominic.
Hmm. Yeah, yeah, yeah. I see. I see. So, Sebastien, let's wrap up this with a moment of engineering camaraderie. I'd like to propose something a bit different to close our conversation. When I say a bit different, a
Okay.
little bit different from the previous interviews I did, a short engineering dialogue between the two of us. As you know, as an aerospace engineer, I spent much of my career working on the structural analysis, particularly, yeah, as I said, on the aerospace sector, where we also deal with extreme load cases, extreme conditions, I should say, and we push toward lighter, stronger, and more efficient design. And your 3,000-meter tower concept today resonates with me, okay? Not just technically, but also in terms of vision. So perhaps we could take 10, 15 minutes to brainstorm together, not to solve it all, it's not possible, but to co-reflect as engineers on how to push our discipline further. I'm curious about your instinctive engineering reasoning. You see what I mean? And I'd be happy to share how I might approach myself, the problem, from a simulation strategy and structural logic standpoint. Are you okay with that?
Yeah, I think I would be more than happy to hear what's your vision, how you feel such a project, and what are your habits, how to solve
Yeah. Okay. Good.
about the
So
design. And
yeah. I have three ideas in my mind. If you do, I want to share with you, and I want to hear your um, your reflections. So how I would approach the structural design of a 3,000-meter tower. The first discussion I would like to have with you is I call that the top-down conceptual strategy. Okay. My instinct would be to begin with the I call that the top-down decomposition, where we consider the structure not as one continuous model, but as a stacked hierarchy of structural domains, each governed by its dominant load mechanism. Compression at the base, flexural, torsional interaction in the midspan, and lateral deflection control at the top. So my question for you, Sebastien, is when considering a 3,000-meter tower, do you foresee a need to divide the structure into different vertical zones, each governed by distinct load-bearing mechanisms such as compression at the base, bending torsion in the midsection, and lateral sway control at the top? How would you define these zones, and how would they influence your design logic at the end?
well, that sounds great. I think you should try to develop the idea and see what it means in terms of design and geometry.
Mm-hmm.
Um, until now, I've been thinking to apply the same equation and framework from top to down. Um, each 40 meters is a new column, so there are 70 times to get to 3,000 meters, right?
Okay.
And I think this discussion is a starting point. Just linked to your question, make me think to different things that are probably great. It's not mechanical resonance, it's idea resonance. That's great.
So now another idea I have in my mind is more related to the FEA modeling philosophy. Okay, from an FEA perspective, I would opt for a multi-scale modeling approach, attempting to represent as we said before, attempting to represent the entire structure at full fidelity. It's not practical. Okay, so I would define a global homogenized shell beam model for overall behavior. In the aerospace industry, we call that a GFEM, a global finite element model, okay? Supported by detailed local models for the critical joints or the transitions, for example, because we know that the joints are always critical in structure. So my question is, given the computational limits you described in your article, how did you approach multi-scale modeling for the tower? Especially, what role do you assign to the global homogenized model versus the local high-fidelity submodels? And how do you ensure consistency between the two, between the global and the local models?
Well, in my case, it's not, well, I couldn't plan how many models I would develop to be able to present something consistent
Okay.
with the community. I think developing multiple models is a good approach in that case. But each model has advantages and inconvenience, right? But the main point is to get a calculation approved by the regulation authorities to get it built. For instance, if you want to do it in Paris, France, you have to comply with our codes, as discussed. or Toronto or Montreal. Um, it would be useful here upfront to know what such authorities would think about it, if it's correct or not in terms of methods, because the designer, well, the design office is not the only um, part of the project, right? But I think the way you proceed to get an homogeneous model is probably the most hard part of the job, because it's not that clear in the literature. I think there are multiple ways to do that, and there's not necessarily a gold standard for that.
Okay.
And actually, I'm still thinking about it. It's not, I don't know. I'll probably talk in the next months and years about that, but maybe you already have some information about that. I'll be happy to hear about that. But I'm also thinking that at the end, we're talking about mechanical structures, calculations, and good practices. But at the end, also small prototypes from 0 to 40 meters could be great to build to confirm various data with the loading test. For instance, you fill a water container and see displacement, and you adjust. You just to be sure what you're doing, right?
Yeah, as we do in the aerospace industry, we do a lot this kind of approach. We use a lot this kind of approach in the aerospace industry. We test a lot, and we use the test result to calibrate the simulation, and then when the simulation is calibrated, we can optimize without testing because we know that we have a validated model. So yeah, I think it's a great idea to use this approach. But to be honest, I'm really convinced that your project is a good candidate for the global model approach, and because the global model approach is consume less degrees of freedom, less powerful than a high fidelity model. Okay, so using a global model, it's as we do in the aerospace industry for a complete aircraft. We model the complete aircraft using a global models. So it's a lot of simplifications for sure, but we control those simplifications. We understand those simplifications. Okay, but it's a great approach because it permits to obtain some boundary conditions and use those in terms of displacements or force at the interface and apply them in high fidelity submodel to solve more complex problems. So I'm pretty sure that your project would be a good candidate for this kind of approach.
And what do you think about what are the risks, maybe the numerical risk in doing various models or different dimensions elements like 1D, 2D, 3D?
Yeah. The risk
is pretty good, or do you think sometimes in certain conditions it can be difficult to get good results? Or
to be honest, for now, I would say, okay. There is always risk to increase the number of model, okay, for sure, because each time you introduce a new model, you introduce a risk of errors, of interpretation, of making a modeling errors, for sure. But now we have a very good knowledge of the modeling techniques. We know what is working and what is not working. So we are able to make sure that each submodel, each high fidelity submodel will work properly. So I think the risk is minimum now with the knowledge we have with numerical simulation.
So in such workflow for the tower, it would need to have a high level of control and review on models.
It is the key. Absolutely. Absolutely. Absolutely, Sebastien.
Engineers, and you have to control they're doing the job with an appropriate method that is.
Absolutely. Exactly. You have to define first all the modeling techniques, all the guidelines that every FEA engineer has to follow. Okay. And from that, as you said, control and verify to make sure that every single submodel is built using those guidelines and those methods. It is the key when you do submodeling and when you use finite element analysis intensively in a project. And to be honest, it is what we are doing in the aerospace industry. we have this level of verification for every single model. Every single model, not only the global FEM of the aircraft, but also every single sub-model, we call them the DFEM, Detailed Finite Element Model. Every single DFEM is verified and validated, okay?
Great.
So
That,
it
that
is
sounds
this
very
approach.
important, Dominique. A very important point.
Yeah. So to conclude this brainstorming, Sebastien, I would like to talk about materials and construction strategy. If I had to design this tower today, I would favor an hybrid material system. For example, by hybrid material system, I mean high strength steel segments at the mid height and ultra lightweight composite models for the top. Did you consider an hybrid material strategy such as high strength steel in the mid-height segment and composite at the top to address the varying load demands along the tower height?
Oh, that's great. Well, I have two, maybe three thoughts about materials. The first was, well, can you find in the industry the materials in sufficient amount, right? For instance, if you,
Yeah.
as I said, well, I think for a 3,000 meter tower, I need 700,000 tons of steel here, without counting the bolts, just steel beams.
Yeah.
And you have different grades, right? You have different resistance.
Absolutely.
So you want to be sure that you can find these grades in sufficient amount because it's.
Yeah.
But if you look at the amount this industry produces each year, for instance, only in France, they produce multiple 3,000 meter towers in terms of weight. It's no problem, right?
Okay.
But if you select some best quality grades, then you, of course, it may be a bit more difficult. You have to extend to Europe to find different partners. But also, if you decide to create to buy multiple grades steel for the structures, then comes the question: how do you manage to be sure that the guys that bolt it at this place of the tower is putting the correct grade, so you can be sure that at some spot there are going to be mistakes. Sure. It's sure.
Yeah.
It's human, just human, right?
Yeah, absolutely. Yeah.
So if they put low grades at the bottom, it might be a problem. If they put high grades at the top, it might not be a problem. So at some point I was thinking, well, maybe it might be safe to use the same grade for the wall structure, but I think for the foundation you need a concrete. As you discussed, we agree on that. That's the point, I think. But what about ultra lightweight composite? This kind of stuff that I'm not used to calculate, so I'm not going to say anything about it. But I think, for instance, on the floors, when people are walking, you clearly want to reduce the load there, because again, you have to control the global weight of the structure. And but I'm wondering, I don't know. For instance, for structural beams, could you use ultra lightweight composite?
Yeah, I think.
How do you link it with the beams, with steel beams? Sorry.
Yeah. I think it's feasible because in the aerospace industry, for example, a few months ago, I worked for a customer on a full aircraft, an aircraft in full composite structure, and even the spars of the wing were full composite. So the spar of the wing are typical C-shaped sections. Okay, the total span of the wing is made of that. And the first time I saw the design of the spars, I was very surprised, because the shape is very complex. It's not a straight beam, because in your case, for a floor, it will be a straight beam. But for this aircraft, it is not a straight beam. There is a lot of kink and variation of thickness and blah, 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 because it's optimized for sure, because it will fly, so it has to be very light. And the manufacturing, they manufacture the part, they verify the part, it's perfect. And it is connected with some metallic parts at some locations. We had to install some aluminum. It's not steel, but it's aluminum, some aluminum subcomponents connected to the composite. And so there are solutions which are working to do hybrid composite / metallic structures. So it is intensively used in the aerospace industry. You see what I mean?
Yeah, of course. One of the questions that comes, well, it's not as a structural engineer, but most as a for business, right, and prices is it's the cost of
Absolutely.
structures.
Absolutely.
For instance, for carbon steels, basically in France, the price is around 800 euros for 1 ton of steel.
Yeah.
Do we have any idea? Do you have any idea, or how? I don't know. Maybe it's not appropriate to discuss this here now, but
Yeah, I don't remember by heart the number, but definitely it's higher than that. It's more expensive. You're completely right, Sebastien. It's more expensive. But after that, the reason why it is used in aerospace, it is because you use less material, and also the performance of the composite is amazing. For an aircraft, it makes a big difference.
Yeah.
Probably for a tower, it won't make a big difference. You're right. But for an aircraft, it makes a big difference between even, we don't use steel, but between aluminum and composite.
I think it's relevant to discuss this. I know steel is very much used in construction as concrete, but it might be a difference for such a height, right?
Yeah.
I don't know.
Yeah.
We'll see.
But I love your idea to consider maybe composite for the floors, because it's a very simple structure, compared to the rest of the structure. The floor, it's a flat structure, so you need I-beam or C-beam with a cover, and even the attachment with the surrounding steel. There are many solutions which I can see are working. Yeah, maybe some things to consider and to think about. So yeah, thank you for those reflections, Sebastien. I really appreciate you accept to be part of this episode of FEA Journeys, and I'm pretty sure the audience will enjoy this episode, because personally I had a lot of fun to discuss with you. And again, thank you very much, Sebastien. And I'm pretty sure we are going to talk in the future about your project, and count on me to follow you on this project. Thank you very much.
Thank you very much, Dominique. Bye.